It's also somewhat obscure, so I'm going to spend much of the talk sort of reviewing why in the world such a statement appears to be true. Then the new thing, the reason for the talk, is that I'll be talking about gauging that one-form symmetry. And gauging the one-form symmetry simply acts as a projection onto components. And amongst other things, I'll walk through the details of mechanically how in the world that actually turns out to happen. Now, there's a secondary theme to this talk, which is somewhat entertaining. Two-dimensional theories with global one-form symmetries have several different descriptions. One description, which is probably the main one I'll be talking about today, is as a gauge theory with a trivially acting subgroup. Trivially acting in all the massless matter of the theory. Another description that sometimes appeared is as a theory with a restriction on instanton sectors, which immediately suggests that these theories could suffer from issues with cluster decomposition. I'll come back to that later. A third description of these theories is as sigma models on gerbs. So a gerb is basically a fiber bundle in which the fibers are copies of the one-form symmetry group, which is sometimes denoted G1, but in this talk I'll be denoting by a BG. So if I have a sigma model on the total space of a principal G bundle, that sigma model will have a global G symmetry from translations along the fibers. And the same thing is true here. If you have a sigma model on a gerb, then there'll be a global symmetry due to translations along the fibers. The only difference here is that the global symmetry is a one-form symmetry rather than an ordinary zero-form symmetry. And then finally, another description that's often popped up in the literature is in terms of coupling a quantum field theory to a topological quantum field theory, which is fine, but it's not something I'm going to have the time to talk about today. So as a secondary theme, one of the things I'll do is discuss explicitly how this decomposition I mentioned into what have sometimes been called universes implements that second description as a restriction on instanton sectors. Essentially, the restriction on instanton sectors pops up as what I laughingly sometimes refer to as a multiverse interference effect, as the contributions from the different universes interfere with one another, which relates some of these pictures. All right, so here's an outline of what I'm planning to do in the next 35 minutes. I want to begin with a brief overview of one-form symmetries and two-dimensional theories. Now, at this point, one-form symmetries are probably, just taken in many quarters to be a staple of quantum field theory, but I've still run into lots of people that maybe aren't always up to speed, so I think a one slide briefly overviewing that seems wise. Then I'll walk through a brief overview of decomposition of two-dimensional theories with finite, global, one-form symmetries. And then in the remainder of the talk, I'm going to focus on one, or if there's time, two simple concrete examples. The first example will be an orbifold with a Z mod 2 one-form symmetry. I'll walk through explicitly how decomposition works in that case, and then I'll talk about how one can explicitly gauge that one-form symmetry. And then if there's time, I'll perform the analogous analysis in a pure non-supersymmetric SU2 Yang-Mills theory. I'll explicitly describe how decomposition arises, how to see it, and then I'll explicitly gauge the one-form symmetry in that context. Now, to be clear, this only scratches the surface. There are more examples, there are more kinds of examples, there are fun applications, but this is a relatively short talk, so I just wanted to focus on a few basic things. Now, what's a one-form symmetry? So again, this is often described in terms of actions on defects, but for this talk, I want to focus just on local quantum field theories themselves. For this talk, intuitively, a one-form symmetry will be a group, or something like a group, that exchanges non-perturbative sectors in, well, in this case, a two-dimensional theory. So for example, if I have a G gauge theory in which the massless matter is invariant, or in which the matter is invariant under some subgroup of G, let's assume it's finite and abelian, then the non-perturbative sectors, the non-perturbative contributions to the path integral are invariant under this permutation of the possible sectors. I can take a G bundle and essentially I'll replace it with that G bundle tensored with a K bundle. And because all the matter is invariant under K, that will give rise to a symmetry of the quantum field theory, just an interchange of the non-perturbative sectors. So this is the one form symmetry involving something that's basically a group of K bundles, and that group I'm going to denote by BK. Now I've put group in quotes there because one should be slightly careful. In an ordinary group, for example, if I take a group element and multiply it by its inverse, I get the identity. In this context, if I take a group, well, a group element, a bundle, and multiply it by its inverse, I get something that's isomorphic to the identity. So instead of having honest equivalences, one only has isomorphisms, and so it's not really a group, it's sort of the next best thing to a group. But that detail isn't really going to play an important role in this talk, but it's worth pointing out. Now, suppose you have a 2D QFT with a finite global one form symmetry. There's an old result that such theories decompose into disjoint unions of theories without a one form symmetry. Now, let's make that concrete. So decomposition, let's do this in two-dimensional gauge theories. Suppose I have a G gauge theory. Let's suppose G is semi-simple with a finite subgroup acting trivially. And for simplicity, let's assume K is in the center and that the resulting one-form center symmetry is not obstructed by some other mechanism, so that the theory has a BK symmetry. So in this case, the claim is that the quantum field theory of that two-dimensional gauge theory should decompose as a disjoint union of quantum field theories of G mod K gauge theories with various different discrete theta angles. So for example, a pure SU2 theory would then decompose as a sum of two copies of an SO3 theory, one with either value of the discrete theta angle. The discrete theta angle just being an analog of a theta angle that couples to a discrete degree 2 characteristic class. In this case, a G mod K gauge theory would have a K valued degree 2 characteristic class, and so we have a set of discrete analogs of theta angles corresponding to characters of K. There's another version of this for analogs of nonlinear sigma models. There isn't time to walk through that today. Now, one effect of this decomposition is to implement a projection on non-perturbative sectors. And so I've tried to illustrate very formally at the bottom how that works. On the left, I have a disjoint sum of path integrals involving just a sum over the possible discrete theta angles. And on the right, I've taken that sum and moved it inside the path integral measure. And when I do so, that sum over discrete theta angles and that weighting of the path integral measure combine to form something that is proportional to a projection operator. And schematically, this is what I mean by decomposition implementing a projection onto non-perturbative sectors. That sum over components, that sum over universes is, at least in this formal argument, implementing a projection operator. Now, since 2006, we've checked decomposition in a bunch of different examples in a bunch of different ways. In gauge linear sigma models, we can compute mirrors and quantum cohomology rings, and the structure falls right out. In orbifolds, we can compute partition functions and massless spectra and elliptic genera, and the structure basically falls right out, as I'll review in an example in a few minutes. You can see this in open string theory. In the context of a gauge theory, just because the gauge group acts trivially on the bulk fields doesn't mean it necessarily acts trivially on the boundary fields. So you get essentially copies of the possible boundary fields indexed by irreducible representations of that trivially acting finite group, as a consequence of which you have a decomposition of the open string sector. You can see this in open string theories via localization. Partition functions, two-sphere partition functions naturally decompose in this fashion. One can play this game in non-supersymmetric pure Yang-Mills theories. I'll briefly outline towards the end, if I have the time, how that works. Nowadays, there's even a version that was worked out recently for four-dimensional theories with three-form symmetries. Let me take just a minute to emphasize that what I'll be talking about is a two-dimensional theory with a one-form symmetry. And I'm not going to talk about other dimensions. If one wanted to talk about other dimensions, well, the type of form symmetry would change. Now, the reason we've done all this is that there are some fun applications of this, or at least fun for me personally. This makes some predictions for Gromov-Witten theory, which were checked in a series of papers starting in 2008. One can use approximate one-form symmetries to understand phases of certain gauge linear sigma models. This is probably my favorite application of these particular things. There won't be any time to discuss it today, but if anyone's curious, ask me later. And this is also pertinent to recent discussions of moduli spaces appearing in string theory. Here, there's not a decomposition story per se, but the same mathematics appears in understanding moduli spaces. Basically, many of these moduli spaces necessarily have some sort of finite gerbe structure, which is reflective of various t-dualities and plays an important role in various things. But that's beyond the scope of what I can do in this talk. Let me mention one other quick example before going on, involving vacua of pure supersymmetric gauge theories. So for a pure G mod K gauge theory in 2 dimensions, for a pure supersymmetric G mod K gauge theory in 2 dimensions, it turns out you get supersymmetric vacua for one choice of discrete theta angle, and supersymmetry is broken for other choices. I've outlined the results here. For SUK mod ZK, for example, there's a Z mod K's worth of choices of discrete theta angle. It's the one given in that first entry, the -1/2 K, K minus 1 mod K, that for which you actually get non-trivial vacua. For that one particular discrete theta angle, the infrared theory is believed to be the same as the original, or as the SUK gauge theory itself, and there are no vacua in the, no supersymmetric vacua in the other, for other choices of discrete theta angle. So this is consistent with decomposition. Decomposition in this case just says that basically the G gauge theory should be equivalent to a disjoint union over G mod K gauge theories. And basically what I'm saying is that the sum of the supersymmetric vacua on the right-hand side matches the supersymmetric vacua on the left. I should also add decomposition is just a structural result in this case. Decomposition does not uniquely predict which theta angle. It doesn't even distinguish other choices. For example, it might have been that the vacua appearing at that one discrete theta angle were actually spread over multiple different discrete theta angles. Nothing about decomposition said they all have to lie in just one, but this is just a structural result. It's yeah. So suffice to say, decomposition seems to be well established, or at least after fiddling with this for years and years and years, I have yet to find a counterexample. If anyone can think of one, by all means, get in touch. I'll be happy to take a look. Now, what I want to do next is walk through a simple example. First, to try to demonstrate why this perhaps obscure looking result actually works, and then to describe how exactly one gauges that one form symmetry in that context, which is the new piece of this particular story. It's in principle the reason I'm giving a talk today. So let's consider an orbifold of a space, some clavial, by the 8-element group D4. Now, D4 has a Z mod 2 center. Let's assume that center acts trivially on the space X. So from what I've outlined before, the theory has a BZ2 symmetry. Now, if I quotient D4 by the center, I get the group Z2 cross Z2. So this theory is going to be closely related to a Z2 cross Z2 orbifold. Now in this context, in this example, decomposition predicts that that D4 orbifold of X should be the same as a sum of Z2 cross Z2 orbifolds, one with discrete torsion, one without discrete torsion. This is a consequence of a general formula, a general prediction for decomposition, which has been written down for analogs of nonlinear sigma models. I'm not going to have the time to walk through the details. If you're curious, ask me later. But suffice to say, it's a consequence of a formula, not just some random observation. Now, let's check that. Let's check it by, for example, computing the partition function. Now to do that, if you'll bear with me for a second, it'll be helpful to actually walk through the possible group elements. So D4 has 8 elements. I'm going to label them 1Z, A, B, and various products thereof. The Z generates the Z mod 2 center. And A and B do not quite commute with one another, as is visible in that table there. If I take the quotient by Z2, what I get is a Z2 cross Z2 orbifold, whose elements I'll label by 1 A bar, B bar, and AB bar, where the overline is just to indicate that one's working with that coset. Now, the partition function of this theory is, let's see, easy to write down formally. For any orbifold, we take the one loop partition function is 1 over the order of the orbifold group times a sum over commuting elements times path integral contributions that look like maps from basically a torus with branch cuts, if you will, into the target space. And I've indicated those contributions by this here. Now, since Z acts trivially, these contributions are symmetric under multiplication by Z. That generates the trivially acting center. So this contribution is the same as that one, as that one, as that one. And the first observation I want to make is that these different sectors are all related by Z2 bundles. One way of thinking about these commuting pairs is that they are defining principal D4 bundles over the 2 torus. I can get from this D4 bundle to this D4 bundle by tensoring with this Z2 bundle I've indicated down here. So these different symmetrically contributing sectors are related by multiplication by Z2 bundles. And this, in this context, is the BZ2 one-form symmetry. Now, so far I've told you that each D4 twisted sector that appears is the same as a Z2 cross Z2 twisted sector appearing with multiplicity 4. There are basically 4 different classes of Z2 bundles I can multiply in, except for these 3 sectors which don't appear. The reason they don't appear is that they do not correspond to commuting pairs of group elements inside D4. If I tried to lift A bar and B bar to a pair of elements in D4, well, the natural guess would be A and B, but A does not commute with B. A and BA is ABZ, it's not AB again. So that cannot appear inside the D4 orbifold. Similarly, these 2 sectors cannot appear either. So this is the restriction on non-perturbative sectors that people sometimes talk about in connection with one-form symmetries. Here we are, this partition function excludes some of the non-perturbative sectors that would have appeared in a Z2 cross Z2 orbifold. Now, computing the partition function, we have that the partition function of the D4 orbifold looks a lot like the partition function of that Z2 cross Z2 orbifold, except we've subtracted out some sectors. And if we're going to be careful, we also need to worry a little bit about multiplicative factors. They turn out to just generate a factor of 2. Now, the next point I want to make, which I think will probably be obvious nowadays, but bear with me, is that this is different than a Z2 cross Z2 orbifold. I emphasize this for historic reasons. When I first started talking about these theories a long time ago, one of the main complaints I got was that surely if the Z2 acts trivially, you're going to get the same result as a Z2 cross Z2 orbifold. There can't possibly be any meaningful difference. So after having fought that battle far too many times over the years, I just wanted to remind everyone that this theory really is different than just a Z2 cross Z2 orbifold. And in modern language, it's because of the existence of that one-form symmetry. Now we can say a bit more. Discrete torsion in the Z2 cross Z2 orbifold is just a Z2, and it acts as a sign on precisely these same sectors, which were omitted above. So a more useful way to write this particular partition function is as a sum of 2 partition functions, a sum of 2 Z2 cross Z2 orbifold partition functions, one with discrete torsion, the other without. Since discrete torsion multiplies the ones to be excluded by a sign, the effect of adding these things together is to cancel out these contributions. And the result matches the prediction of decomposition I mentioned earlier, that the conformal field theory of that D4 orbifold should match the sum of the conformal field theories of the 2 Z2 cross Z2 orbifolds. Now, let me tell you a few more things about this before going on. At the level of operators, one reason for this is the theory admits projection operators. If I hat denotes the dimension 0 twist field associated with that trivially acting Z2, then I can build a projection operator onto either of the 2 components, or I can build projection operators that look like this. And that's one way in terms of local operators to see why there are 2 components. In terms of massless spectrum, well, we can compute the massless spectrum of the D4 orbifold. It's straightforward, but the first time I saw it years ago was a little bit confusing. Here saying I'm computing the massless spectrum, I've taken X to be T6. I've let the Z2 cross Z2 act as pairs of sign flips on 2 tori inside that 6 torus. So this is closely related to a old standard example of a toroidal orbifold, a 6 torus modulo as Z2 cross Z2. If I do this for the D4 orbifold, I get this. It's got more stuff than the massless spectrum of a Z2 cross Z2 orbifold, basically because some of the non-perturbative sectors were omitted, so the projection operator in the orbifold is weaker than it would have been. I've arranged the result into a Hodge diamond. I work on string compactification, so it's a natural thing for me to do. And these 2's in the corners are a good signal that whatever this thing is, it's trying to behave like a disconnected space. It's trying to behave like 2 copies of a space, not just one space. And indeed, if you compare the spectra of Z2 cross Z2 orbifolds with or without discrete torsion, they take these forms here, and it's easy to see that adding these together gives the D4 orbifold spectrum. So again, that's consistent with the prediction of decomposition, that the D4 orbifold should be the same as a pair of Z2 cross Z2 orbifolds. Now, all of that was new. Let me try to get to something that's, or all of that was old. Let me get to something that's actually new. Let me describe how to gauge that BZ2 in this context. So in broad brushstrokes, what should gauging that BZ2 one form symmetry look like? Well, the partition function should look like 1 over the order of, if I'm going to gauge a BG, I would expect that the partition function should look like 1 over the order of G times some sum over G gerbs of sectors twisted by the G gerb in the sum. So I've got some path integral over BG non-perturbative configurations, if you will, and then in each of those I have something twisted. So in this case, I have a BZ2 I want to gauge. So I have a 1 over the order of that Z2 times a sum over gerbs, banded gerbs, it turns out. There's a more general class of gerbs which don't arise in the sum. If anyone's curious, ask me later. Here is the sector twisted by the gerb. This looks like the partition function of a D4 orbifold, except that the bundles appearing are all bundles that are over a gerb on T2 rather than over the T2 itself, which means as a practical matter, the G and H only have to commute up to multiplication by Z. And then finally, there's a phase we can add to weight these contributions differently. It's some analog of discrete torsion that arises in this context. Now, again, these GHZs are gerb twisted, orbifold twisted sectors. That's a mouthful. If anyone has a better name for it, let me know. For Z in the center of the orbifold group, SL2Z will map a sector like this to a sector of the same form, preserving Z. For more general Z's, modular transformations will map Z to a conjugate. That's beyond the scope of what I can talk about in this talk. Finally, these phases, epsilon, are constrained to form a group homomorphism from Z2 into U1. That's partially as a result of multi-loop factorization. Now, let's put this together. So suppose we take Z to be 1. Then in the contribution from Z to where Z is 1, this is just the ordinary partition function of the D4 orbifold, which, as mentioned before, looks like twice the partition function of a Z2 cross Z2 orbifold minus some sectors. In the sector where Z is different from 1, this is just a Z2, so there's only one such sector. Well, the only contributions are going to be from group elements that commute up to the action of Z, and the only possibilities are these 3 here, which turns out to be exactly in one-to-one correspondence with the sectors excluded from the Z2 cross Z2 orbifold. So now you can probably sort of guess how this is going to work. If I want to construct the partition function of the D4 orbifold in which I've gauged the BZ2, I'm going to add these 2 possible contributions weighted by the epsilons. Now, since epsilon is a group homomorphism, epsilon1 is equal to +1. The interesting value is epsilon at -1, epsilon on the non-trivial element of Z2. In one case, the effect of adding these together is to cancel out these two terms. So if this phase is equal to +1, then I recover precisely the partition function of the ordinary Z2 cross Z2 orbifold. If this phase is -1, then the effect is to essentially subtract this twice. So these sectors appear, but now weighted by a minus sign, which means that's the partition function of the Z2 cross Z2 orbifold with discrete torsion. All right. Now recall decomposition in this case. Decomposition said that the D4 orbifold should be the same as two copies of a Z2 cross Z2 orbifold, one with discrete torsion, one without. We got both of those possible objects as consequences of gauging the BZ2. There was a choice in this particular phase, this analog of discrete torsion. The upshot is that gauging that one form symmetry has projected onto the components. So that's a fun game in orbifolds. I think I've got enough time to quickly walk through one more different kind of example in which this happens. Let's consider a pure non-supersymmetric SU2 Yang-Mills theory. So in a pure non-supersymmetric SU2 Yang-Mills theory, there is on the face of it a global BZ2 center symmetry. Decomposition predicts that SU2 theory should be a sum of a pair of SO3 theories, one with either value of the discrete theta angle. So in terms of partition functions, this is straightforward to check. From McDowell and Rusikov's old work in the late 80s, the partition function of the SU2 gauge theory is a sum of this form in which we sum over all SU2 representations. For the SO3 plus theory, the SO3 theory with no discrete theta angle, you have what looks like an identical sum, except that it only involves SO3 representations rather than SU2 representations. Now to see this, we need the partition function for the SO3 minus theory. That was essentially worked out by Yuji Tachikawa back around 7 years ago, and Yuji's conclusion was that the partition function of the SO3 minus theory should look, well, basically have the same form, except you should sum over all the SU2 representations that are not SO3 representations. So the effect of turning on the discrete theta angle is to sum over representations of the covering space group with the right anality. So the result then is the partition function obviously decomposes. A sum over SU2 reps is the same as a sum over SO3 reps plus a sum over the remaining SU2 reps. And in fact, this is easy to generalize. So let's see, more generally, if I have some pure non-supersymmetric two-dimensional G Yang-Mills theory, and G has center K, then one expects a decomposition of this form, of the G gauge theory into a sum of G mod K gauge theories, where the thetas are discrete theta angles coupling to analogs of Stiefel-Whitney classes. There's a similar decomposition that's easy to write down for the Hilbert spaces. The Hilbert space of a pure G Yang-Mills theory is the L2 class functions on G, and these have some natural decomposition under the action of the center. The Hilbert space, one can argue for the G mod K gauge theory with discrete theta angle theta, consists of those particular L2 class functions on G that transform like this under the center. And so for essentially trivial reasons, it's easy to see that the Hilbert space of the G gauge theory is a sum of the Hilbert spaces of the G mod K gauge theory. Now, let's see how to project, let's see how to gauge BK. What does it mean to gauge that BK center symmetry in this particular context? So broadly speaking, much as before, the partition function of a BK gauged gauge theory should have this form: 1 over the order of K, a sum over K gerbs on the world sheet, some phases, some analogs of discrete torsion, and then the gerb twisted contributions. So these z's are the partition functions. ZZ is the partition function in a sector twisted by a k-gerb of characteristic class Z. Now, to define the gerb-twisted gauge theory partition function, if you've seen the old McDowell-Rusakov way procedure, basically is going to involve coming up with some sort of twisted cap. So the game they play is to come up with functions to associate to various pieces of Riemann surfaces with group elements associated to components of the boundary. So for an ordinary cap, the corresponding function, the contribution from that cap looks like this, a sum over pertinent representations of this function. This is a character of the group element corresponding to the Wilson line along the boundary, and the representation R, the one summing over. The partition function for a two-sphere can be obtained by taking two of those caps, sticking them together, and then integrating out the Wilson line along the joint boundary. The result looks like a sum over representation. Well, the result is the special case of what I wrote down before for genus 0. A twisted cap is very similar. The difference is instead of having just the character of U, we have the character of U times Z. And the effect of that is to pull out some other phase factor. So putting this together, the partition function of that pure G gauge theory in which the BK has been gauged is again a partition function of this general form. Plugging in Z of Z, plugging in epsilon, one gets an expression like this. This sum over gerbs becomes a projection onto representations of fixed anality determined by the, essentially the choice of phase epsilon. And then with that particular representation, the result is a sum over what looks like the same partition function as before, except now with a restriction to representations of the covering group of a particular fixed anality. In other words, it's the partition function of the G mod K gauge theory with discrete theta angle lambda. So the effect of gauging that BK with a phase determined by lambda is to select one component of the decomposition of that two-dimensional pure non-supersymmetric theory. All right, so far I've reviewed decomposition, which I emphasize is, in my talk, has just been a property of two-dimensional quantum field theories with a finite global one-form symmetry. And I reviewed how to go about gauging that one-form symmetry. So what about quantum field theories in other dimensions? So for four-dimensional theories, Yuya Tanizaki and Mehmet Unzel worked out an analog of this past December in four-dimensional theories with a finite global three-form symmetry. There's a natural conjecture here they speak about a bit that there should be some analog of this for quantum field theories in D dimensions with a finite global D-1 form symmetry. I don't think any of us have really worked through a lot of the details of that, but it's sort of the natural extrapolation of examples in these two sets of dimensions. And along that spirit, one can say a little bit more. If that's true, it's going to involve a D-1 form, and part of what's going on is that D-1 form will couple to a domain wall. So one ends up with something that's somewhat analogous to the old Busso-Polchinski picture years ago for nucleating membranes in four-dimensional theories to reduce the cosmological constant. It's analogous in the sense that one would have, in the four-dimensional case, a three-form coupling to a domain wall. There's no cosmological constant. There's no four-form with a non-trivial kinetic term that dynamically drives membrane nucleation, but at some level it's analogous. This is also consistent with reduction on a circle. That D-1 dimensional theory would have a, if I reduce on a circle, I get a D-1 dimensional theory with a D-2 form symmetry, which, if the conjecture is correct, would decompose. And furthermore, if the d-dimensional theory decomposes, then surely its reduction on a circle has to decompose as well. So is there any math here? This is a conference, this is a string math conference, and I think I've managed in most of this talk to speak only about the physics side of all of this. Let me, here at the end of this talk, briefly talk about corresponding mathematics, or at least place this in the world of mathematics. So far I've just talked abstractly about two-dimensional theories and one-form symmetries. So this can be interpreted mathematically in terms of gerbs. As I mentioned very briefly earlier, a G-gerb is basically a fiber bundle where the fibers are copies of that group of one-form symmetries. Furthermore, a sigma model on a G-gerb should have a global BG symmetry, just as a sigma model on the total space of an ordinary G bundle would have a global zero-form G symmetry from translations along the fibers. Furthermore, one representation of BG is as the quotient of a point by G. So, I mean, a good intuition is whenever you have a gauge theory in which a group is acting trivially, then the gauge theory is trying to implement this over every point of the Higgs branch. And so it's sort of natural to expect that there ought to be some sort of gerb structure or one-form symmetry lurking somewhere in the theory, unless it's been obstructed for some reason. Now, 20 years ago, I got into this because I was interested in studying sigma models on gerbs as possible sources of new string compactifications. There were a lot of headaches at first. There was, well, initially some question about how in the world you actually build a field theory that would correspond to this. There are questions about how cluster decomposition works, as I've touched on earlier in this talk. There were confusions about moduli. The moduli of the gerb, the moduli of the stack are not the same as the moduli of what one would expect is the corresponding physical theory. So there's a headache about why the moduli don't match. There are potential questions about modular invariance and unitarity and orbifold examples. There are issues with potential presentation dependence. Suffice to say, what we eventually learned was these theories are well defined, but because they're disjoint unions of ordinary theories, at least in 2-2 supersymmetric cases, but they're disjoint unions of ordinary theories, at least in 2-2 supersymmetric cases, because of decomposition. So we don't really get new string compactifications, but instead we do have some other fun offshoots I mentioned at the beginning. There are some predictions for Gromov-Witten theory, which were checked years ago. There are some fun games one can play with GLSM phases, which is certainly my favorite application of all of this. So finally, let me conclude with just a very quick schematic of why gauging BG in a theory with a one-form symmetry ought to result in an ordinary theory. Very schematically, a G-gerb is just a fiber bundle in which the fibers are BG. So locally, it's X cross BG. Gauging BG amounts to quotienting out the BG, which morally ought to leave you with something like X. Now, that doesn't account for non-trivial gerbs, these analogs of discrete torsion, or any of that, but if you forget everything else from this talk, this is a sort of quick and dirty way of understanding where it's coming from. So to summarize, I gave everyone a brief overview of one-form symmetries and two-dimensional theories. I've reviewed decomposition of two-dimensional theories with one-form symmetries, and I worked through a couple of simple concrete examples, in both cases giving an explicit description of decomposition and explicitly gauging that one-form symmetry, which is essentially the new wrinkle, and at this point more of a bookend to this particular line of thought. Last but not least, let me mention we're running an online workshop on gauge linear sigma models in the middle of August. If anyone is interested, you are welcome to participate. Let me again thank the organizers for inviting me and thank the audience for listening to me. That's it.
Thank you. I actually don't know how to unmute all, it seems.
I've done it.
Okay, so if everyone wants to thank you. And so let me mute everyone again. And so, sorry, can you unmute yourself again, Eric? So there's a few questions. Yes, sorry, it's just that I mute everyone and I wanted to unmute you. So we have one question already for a while, sorry, from Xing Tung Yao. Please, can you unmute yourself? Oops. So can you unmute yourself? Do you still have a question?
No, I actually did not ask any question.
Okay.
Sorry. I'm not planning to ask any.
So now then Gregory Moore, sorry. Can you unmute yourself, please? Oh, sorry, I can unmute you. Yes? Sorry. I seem to be.
Okay.
Okay, so now I can, sorry.
I was unable to unmute myself before.
I was unable to unmute you for some reason as well. So some
Okay, well,
glitch.
okay.
Yes.
So Eric,
Sure.
hi. I like to think of quantum field theory, at least conceptually, in terms of a functor from Bordism category to some other category.
All right.
It's a nice picture, but this idea of decomposition, disjoint union, or sums, or universes, quantum field theories doesn't seem to play that well with that notion. So if you have this kind of a Tia Siegel et al. Picture of what a quantum field theory is as a functor from a geometric Bordism category, perhaps with other structures, to some other category, then in general, the direct sum is not going to make sense, and probably that's even true in the examples that you showed. So I just want to ask if that worries you. I mean, to me, it would seem that I'd like to preserve that kind of picture and perhaps expand the notion of fields.
Well,
I'm interested in how you.
I'm open to suggestions, Greg. I mean, this was, when I first started playing with these things, this wasn't an interpretation I came to lightly, I guess you might say. But the reason the thing I like about it is it gives a simple explanation for all the concrete computations I can do. So here in these simple examples, I've illustrated partition functions. I've spoken a little bit about Hilbert spaces. This applies to other cases. If you can compute the elliptic genera follow the same pattern. The quantum cohomology rings follow the same pattern. This even shows up in the mirrors. Now, I'm willing to believe that there's some other interpretation for it. If you can find an extension of the idea of fields that makes this work, I'm sort of game. I think way back when we first computed the mirrors, one of the weird things that pops up in the mirror, if you try to follow the Horry-Boffa prescription, is that you get, what at first looks like some sort of Z mod K valued field. And perhaps that's the extension of fields that you have in mind. But the thing about something that looks like a Z mod K valued field, in other words, a path integral trying to sum over roots of unity, is that seems to be functionally equivalent to having a sum of partition functions. I'm open to other suggestions, but I think my philosophy at this point is if you can find some other description that has all of the properties I've described, if you can find something else such that the massless spectrum of the theory decomposes as if it were a sum, something else such as the partition functions decompose in a sum, the elliptic genera decompose in a sum, the state spaces seem to decompose in a sum, something else with projection operators, something else with the quantum cohomology rings playing this game, something else with the mirrors doing this, something else in which the open string sectors naturally fall apart. If you can find another way of describing it, I'm all ears.
Well, we certainly, I mean, it's not unusual to find sums over topological sectors. And I mean, when I say extension of field, what I have in mind is a point of view that I've learned from Dan Fried,
Okay.
is that you should really think of local, something like an orientation or a spin structure is really a local thing.
Okay.
You consider it as a field, a general notion of a field. And
All
in
right.
particular, another thing I've learned from Dan is that if you have two-group symmetry, which is what you're talking about here, then what it really means is that you have a non-trivial fibration of your space of fields. So
walk me through this real quick. When you say a non-trivial fibration of the space of fields, you mean it's over those different components?
Well, this is going to, okay.
Yeah, but
And that comment would take us too far afield. But I just want to say,
okay.
Suspect that one could, it doesn't really make sense to take a sum of field theories in the sense of Atiyah and Siegel et al. But B, that in your examples, perhaps by expanding the conceptual notion of what a field is, one could fit your decomposition of theories into the Atiyah Siegel et al. Framework.
Yeah, again, I'm game. What this might be, let me get my glasses on and see what the time is.
Yeah,
this might be something that would be best discussed later, just for sheer.
in the breakaway sections.
Yeah, for example. I'm happy to play this game. I am happy for other interpretations. It's just that, in the actual concrete computations I do, everything's consistent with this picture. There's one other point, which is, there's one other point. If I'm not certain I understand the fibration over the fields that you were referring to earlier, but if it's what I think you're referring to, then I think you might be thinking about the components in the wrong way. The different components aren't.
We can talk about it later.
Let's talk about it later. I don't think there's time now.
So
but
now
I'm game. I'm happy to believe there are other interpretations. It's just that for years I keep doing computations. We get results that are consistent with this. And if I don't go that route, then the results become very confusing very quickly. The mirrors don't make sense anymore. They seem to explicitly fall apart. The quantum cohomology rings. I mean, I'm happy to play other games, but if this is not true, then I've got a whole pile of results that I don't know how to interpret usefully. I'll put it like that.
But maybe we still have a few more questions. So
Okay.
the next question, thank you. So the next question is from Nathan Seiberg. Oh, sorry. I just, unmute.
Okay, can you hear me?
I can hear you.
Yes.
I have a more lowbrow version of the same question. So we're
Okay.
in 1+1 dimension, so space is a circle. And
Okay.
the question is there an operator in your theory that acts on all of space that maps you from one of your sectors to the other?
No.
No?
And I can say that because I can build projection operators. Sorry?
At least in some of the examples you presented, there is such an operator. The
Really?
operators that are charged under a one-form symmetry are lines. And if there is a line operator, so there must be charged line operators. And a line operator acting on all of space is going to map us to another sector. I can go through any one of your examples and do that. So it seems to me that the theory with the one-form global symmetry indeed has sectors, but these are not decoupled theories because the spectrum of operators in the theory includes well-defined good operators. They're not at the point operators, but line operators that map us from one sector to another. And that interpretation, I think, is much more conventional.
Yeah, let me think about this for a second. I think you may well have a point. This is, so I prefer to think about just ordinary local operators. And on the ordinary local operators, there are projection operators I can build. For example, in that Z2 and the D4 orbifold example. Yes, if you include Wilson lines, I mean, the thing that's puzzling, the place this might go wrong, in the D4 example So as a simple toy model of, I could imagine a map from, I could imagine a string twisted sector with a, trivially acting Z mod 2, essentially a Z mod 2 twist field in the middle. So that sounds, if I could build a Wilson line out of that, bear with me for a second.
Maybe I should give you a
we should talk
simpler
about this
example.
at greater length
I
later.
think
But
all this D4 is non-abelian and is unnecessarily complicated. The simplest example is just to look at the case where you have an ordinary Z2 global symmetry, spontaneously broken, so we have two vacua. But at low energies, there are only two ground states. This happens, for instance, in the Ising model in the broken phase. I would say that in finite volume, there are two states, and there are operators that map us from one to the other. At infinite volume, the ordinary Z2 is spontaneously broken. And yes, I think this is all you have. These are not decoupled theories. At low energies, they become decoupled. But if you include the line operators that connect them, then they are not decoupled.
So basically what you're
describing
your super selection sectors. So if I'm following you correctly, and I might not be, but if I'm following you correctly, you're talking about super selection sectors. Is that right? Do you agree?
Everything is in finite volume, so we don't even the notion of
good. That's okay. Good. That's because that was going to be my complaint.
Right. So we are in finite volume, and we have a standard quantum mechanical system with a standard looking Hilbert space. Nothing funny here. You don't need to break the rules of standard quantum mechanics and field theory to accommodate this.
Yeah, except this is. Let's talk about it more later. You may well have a point. There are a couple of things that, let me mention three things because I think I'm just about out of time. One is that you're not talking about super selection sectors, but if you were, then I would refer you to Yuya and Midhat's paper from last December, which explicitly looked at super selection sectors in these theories and argued that what's going on is a stronger version, stronger than ordinary super selection, that there are no they couldn't see any, they had an argument that there were no field configurations that the path integral would sum over which related the different universes. The second point was that if you had just a string twisted sector, a string in that trivially acting Z2 twisted sector that actually, when you apply the projection operators, looks like a pair that decomposes into a union of two strings just mapping each of the universes to itself. It doesn't actually connect them. There's a confusion about what the universes are. They're not the same as twisted sectors. There's some linear combinations, which makes that story work. And there was a third point I'm blanking on, but I think I'm just about out of time. So yeah, you may have a point. Let's chat about this some more later. I'm happy to believe, as I told Greg, I'm happy to believe that there is some alternative or more subtle interpretation of what's going on. It's just that in all the computations that I've been doing for years and years and years, everything is consistent with this particular interpretation. You know, I'm happy to believe you may well be onto something, but then we need to have a much longer discussion about, oh Lord, about how all these other computations are then consistent in that context and what exactly they mean.
So perhaps this is a good conversation to have in the breakaway. I think that there's 1 more minute for one last question. Sorry. So it's Hank Chen.
Hi.
Hi.
Hello. Can you hear me?
Yes.
Yes, I can.
Okay. Thank you for the talk, Eric. It was very enjoyable. So I guess my question is, like, what this decomposition looks very much alike is there's something called dimensional reduction in condensed matter, where you sort of reduce your the space of your ground states to conjugacy classes. And that sort of tells you how you can decompose, for example, 3D phases into direct sums of 2D phases. And if this analogy sort of holds, right, then what we can actually look at from just Wen's perspective, what we can look at is the fusion between, for example, if you have Z4 magnetic gauge fields and Z2 electric gauge field, we can look at the fusion between these two excitations, and they have, for example, codimension 1, codimension 2. I'm just wondering if you've ever like, is there a analogous picture that you can have in what you're doing?
I think we should probably have a longer discussion later because I don't understand condensed matter physics nearly well enough to be certain that I'm familiar with what you're referring to. Certainly in the dimensional reductions I'm familiar with, there is some ambiguity about how exactly to go, for example, from a three-dimensional theory to a two-dimensional theory. There is a lovely paper written a few years ago by Over Haurani, Brian Willett, and one other individual whose name I'm forgetting, who looked at this sort of issue. And they argued that depending upon how exactly you take the limit, you can indeed get two-dimensional theories, which are disjoint unions, sums of two-dimensional theories. From a given three-dimensional theory. That sounds like it's what you're describing, but again, I'm not expert at condensed matter physics, so I don't want to swear that that's the same thing. But in any event, let's definitely chat later. If not in a breakout room, then in some other context, I'll be happy to, drop me a line. I'm happy to chat.
Okay, sounds good. Thank you.
So thank you for all the questions, and thank you, Eric, for the very nice talk. And we just have time now to introduce the next speaker, who's going to be Tudor Dimoft from UC Davis in Edinburgh. Can you? Hi. Okay, can see you, and can you share your slides?
Let me try to do that.
So, and he'll be talking about 3D mirror symmetry and home fly homology.
Yep.
So we still have maybe 2-3 minutes, so but perhaps it's better just in case someone is actually coming for your talk. So let's just wait a moment. So you can, I think that it should be fine. You should be able to move the slides and everything. So I guess then after all, we had time for yet one more question. Sometimes it takes a bit longer to set up.
Yeah, teaching a 10-week course this past spring on Zoom sort of makes things run much more smoothly.
Yeah, everything is all set up to already. Yeah, was it like that the first time?
No. There is a lot of trial and error.
Yeah, we just have just less than a minute, and I'll introduce you again if you don't mind.
Yeah, that sounds great.
Just one comment is that if anyone is interested, there's a discussion of the talks going on in the chats. So if you look at your chat, probably you'll see discussions from the previous talks.
And how are the breakout sessions working afterwards, or will you explain that?
I think that Jeff will explain that just after your talk. Exactly. So you